Engineering, Electronics and Telecommunications is hereby convened on December 22, 2025. All 9 listed as members of the Dissertation Council are present. A quorum is established. So according to the protocol, I should list all the members of the Dissertation Council. First, Voshkar Kvantai, Chairman, Doctor of Philosophy, PhD, Professor. Second, Turikhanova Kunduz, Scientific Secretary, Candidate of Physical and Mathematical Sciences, Associate Professor. Third, Jumagulova Karlgash, Deputy Chairman, Doctor of Physical and Mathematical Sciences, Professor. Fourth, Boligenova Saltanat, Member of the Dissertation Council, Doctor of Physical and Mathematical Science, Professor. Fifth, Serebryansky Alexander, Reviewer, Doctor of Philosophy, Lead Researcher, Fesenkov Astrophysical Institute, Almaty, Kazakhstan. Alina Dana, Reviewer, Doctor of Philosophy, Assistant Professor of the Department of Physics, Nazarbayev University, Astana, Kazakhstan. Labadia Bats Jonathan, Temporary Member of the Dissertation Council, PhD, Research Associate, Department of Space Research and Space Technology, DTU Space, Kongens, Lyngby, Capital Region, Denmark. Kim Vitali, Temporary Member of the Dissertation Council, Candidate of Physical and Mathematical Sciences, Lead Researcher, Fesenkov Astrophysical Institute, Almaty, Kazakhstan. Abdikamal Yernazar, Temporary Member of the Dissertation Council, Doctor of Philosophy, Associate Professor of the Department of Physics, Nazarbayev University, Astana, Kazakhstan. Proposal to open the meeting of the Dissertation Council. Are there any objections? Okay, if there are no objections, I hereby declare the meeting of the Dissertation Council open. So, agenda: defense of the dissertation series of articles by Gabitova I.A, entitled Structure and Evolution of Circumstellar Matter in B stars for the degree of Doctor of Philosophy, PhD, in the educational program AD-05307, Physics and Astronomy. The dissertation work was carried out at the Department of Electronics and Astrophysics of the Al-Farabi Kazakh National University. Scientific supervisors. First, domestic. Khakhlov Azamat, Doctor of Philosophy, PhD, Acting Associate Professor at the Department of Electronics and Astrophysics, Al-Farabi Kazakh National University. Second, Foreign Supervisor, Miroshnichenko Anatoly, Doctor of Physical and Mathematical Sciences, Professor of the Department of Physics and Astronomy, University of North Carolina at Greensboro, USA. So the dissertation work series of articles is submitted for defense for the first time. All dissertation materials are available to the members of the council. Are there any comments on the agenda?
No.
Okay, no comments. The agenda is approved. So to familiarize the council with the candidate's personal file, the floor is given to the Scientific Secretary, Turikhanova Kunduz.
Thank you. Dear members of the Dissertation Council, please allow me to account you with the dissertation materials of Gabitova I.A. First document is the application addressed to the Chairman of Board Rector of Al-Farabi Kazakh National University for the acceptance and the submission of dissertation work for defense. Second dissertation work is a series of articles printed and on electronic media, CD-ROM, form of defense series of articles. Third, information about the doctoral candidate, Gabitova I.A was born on the 31st October in 1996 in Almaty, Kazakhstan. And between 2016-2020, she completed bachelor degree at the Tomsk State University, Tomsk, Russia, with a major in physics. And between 2020 and 2022, completed a master degree under the educational program Physics and Astronomy at the Al-Farabi Kazakh National University. Between 2022 and 2025, she completed a doctoral program PhD under the educational program Physics and Astronomy at the Al-Farabi Kazakh National University. And the first document is the certificated personal information sheet of Al-Farabi Kazakh National University's employee. And the fifth is a certified copy of transcript in 3 languages confirming completion of doctoral program. And the next references from domestic and foreign scientific supervisors certified at the respective places of work. And the seventh is the extract from protocol of department meeting containing a positive assessment and a recommendation for the work to be defended, approved by the member of board vice rector for science and the innovation of Al-Farabi Kazakh National University. And the next is reviews from the official reviews certified at their respective places of work. And the ninth is the extract from protocol of meeting of academic council of Al-Farabi Kazakh National University on the approval of the dissertation topic and the scientific supervisors. And the 10th extract from the order of chairman of board director of Al-Farabi Kazakh National University on submitting the dissertation for defense. 11th, it's a list of scientific publications certified by the academic secretary of Al-Farabi Kazakh National University. And the 12th, it's a conclusion of the university's local ethical commission. Based on the dissertation result, 4 printed works have been published, including 3 publications in journal indexed in the scopes and the Web of Science, date-wise 3 papers on the Q2 journal. And she is first authors in the 2 articles of them. The materials submitted by Gabitova I.A comply with the approved rules for preparing dissertation for defense established by the Committee for Quality Assurance in Science and Higher Education of the Republic of Kazakhstan. The dissertation series of articles is approved for defense.
Okay, thank you.
Do you have any questions about the information? Okay, thank you.
Okay, if there are no questions, the floor is given to Gabitova I.A.
Okay, thank you. The introduction was made, so let me get started right away. And the goals of the study was to determine the companion disk interaction in B binary stars by setting and meeting the following objectives: measure V-on-R ratio and establish its relation to the orbital motion, determine and refine fundamental parameters of the system under study by spectral analysis, some modeling, and finally construct and interpret Doppler tomograms to identify and characterize companion-driven disk structures. Now, let me set some context. First, the objects of my study are B stars. B stands for spectral class, and E stands for emission. Now, when it comes to emission, we assume some kind of circumstellar environment. So in this case, it will be a disk that is formed around a B star. The important note is that this disk is not an accretion disk. It is a decretion disk, meaning that B star sheds the matter around itself and forms the disk. Now, if a B star is a binary, which not all of them are, the second star I will call the companion. And the main question of the study is how, without direct interaction, without like accretion process, the companion star is influencing the decretion disk around B star. The main method of the study is called Doppler tomography. It was first introduced in the year 1988 by Martian Horn, and the idea is as follows: we can observe a spectral line. It's an emission and usually double peak line. Let's say it is H alpha. So we know the laboratory wavelengths, and we can assume it as 0, and then we can measure Doppler shift regarding that 0 point. The components of the line have their own Doppler shift, and the line itself can be shifted to the right or to the left. Now we can take this measured velocity and construct a 2D velocity map, which has velocity y and velocity x components. Then we get a density distribution of the matter inside the disk. So if we assume this is a hydrogen line, and we assume that disk consists mainly of hydrogen, then we get distribution of emitting hydrogen atoms in the disk. To the right, you can see a spatial distribution, and you can compare it to the velocity map. Since we don't know tangential component, we only know radial velocity. There is no direct unique transformation from left to right, but you can compare. And it is important to notice that since we measure velocities, the bigger velocities will be actually closer to a star, meaning it is actually inner edge of the disk, this big circumference, and the smaller circumference will be outer edge of the disk. The stars are positioned if we know their mass ratio and inclination of the system. The center of coordinates will be mass center of the system, and companion star will be slightly higher than the B star. To apply Doppler tomography to an object, we need to cover by observations the whole orbital period. Because there are non-uniform density structures in the disks that at some phases we see them as observers, and at other phases they are abstracted from our view. And that's why this work is unique, because the objects under study have orbital period of months, so we needed years of observations to perform Doppler tomography on these objects. And the first object of my study is called Kappa Draconis. It is a B binary. It is a pretty bright star and well studied, so we actually know a lot of its parameters. But important for this study is that its disk, the circumstellar disk around the B star, is dissipating over the years, and then it's reappearing again. So we were able to observe it throughout full dissipation event and explore it. And my first defense statement is that in this object, the phase synchronization of the H alpha line peak ratio, V on R, with the orbital period is called by the companion star influence on the circumstellar disk throughout the entire disk dissipation event, from maximum intensity to complete disappearance. Now, what does disk dissipation look like? You can see on this big plot. This is H alpha line, which is an emission. Emission comes from the disk, and we can see that the line is quite strong at the beginning of observations, and then as years go by, it becomes smaller and smaller until it goes fully under continuum. So in the last year of observations, we see mainly absorption, which comes from photosphere of the star, and the disk component becomes very small. On the right upper plot, we can see the same process, but measured by equivalent widths of H alpha, which is which shows how strong a spectral line is. So we can see a very steady, stable decline, almost perfectly linear. And the V-on-R ratio I talked about is very simple to understand. So we have a double peaked line, and we can measure the intensity of the left peak, and we call it V for violet because it's blue shifted, and we can measure the intensity of the right peak, and we will call it R for red because it's red shifted. Now, as you can see, depending on the date of observation, the one peak will be bigger, and then on another date, this peak will be smaller, the other one will be bigger. How does it relate to orbital motion? On the upper plots here, we can see a radial velocity curve taken from absorption lines. Absorption lines, they come from a photosphere of the B star, so they trace orbital motion of the star. And radial velocities, if we search for periodicity, the dominant period will be an orbital period. And if we fold the data with this orbital period, we will get this sinusoidal curve. So then we measured V-on-R on the same spectra over 10 years and performed the same process, search for periodicity using different methods, Sloan-Scarlett, phase dispersion methods, and they confirmed that the dominant period is matching the orbital one. So when we fold the V-on-R dataset, we get the sinusoidal curve that looks quite the same as the upper one tracing orbital motion. So this means that emission that is formed in the disk is modulated by orbital motion in the system, meaning by the companion star. So we were able to refine parameters. They were known before us, but we got better uncertainties. And here I show parameters of both stars in the system that were done by interferometrically resolving the system by Clement et al. In the year 2022. So I just want to note the mass of the companion, which is 0.4 of solar masses, and the radius of the companion, which is like 0.7 of the solar. So conclusion on the first defense statement is that the V-on-R intensity ratio was measured over almost a decade of observations throughout disk dissipation, and independent periodicity search tests showed that the dominant period in this dataset matches spectroscopic orbital period. So if we fold the V-on-R with orbital period, we will get a stable and repeatable sinusoidal curve, which is not affected by disk dissipation. This allows me to conclude that V-on-R modulation is tied to orbital motion of the circumstellar disk by the companion throughout a decade of observed dissipation. Now, the second defense statement is related to Doppler tomography of this system. And according to Doppler tomography, this phase-locked V-on-R variation arises from bright emitting region in the outer disk that is always facing the companion star. And this region is stable. It exists throughout the dissipation, so it exists due to either tidal or radiative influence of the companion star. And the disk contracts from 64 solar radiuses to approximately 30. So how does it look like? Here we can see the observation split into three data sets. The first period is when the dissipation has just begun, so the disk is strong. And then we are in the middle of dissipation. It is actively going on. And then we're looking at the end of the disk dissipation when disk becomes small and eventually disappears. So let's remember that velocity maps are kind of inside out. And this green circle shows us tidal radius, which is maximum radius that disk can have. And here we see that the emission region is right on the edge of this tidal truncation radius. And then as disk dissipates, it goes under the kind of inside tidal truncation radius, and then it is fully insided. But the position of this emitting region always remained oriented to the companion star. So to understand this better, let's look at more familiar spatial distribution. It was reconstructed like modeled from Doppler tomograms under assumption of Keplerian motion. And here we can see that at the beginning, the emitting region was at the crossing of Roche lobes, so possibly even overflowing out of the disk. And then as disk dissipated, it becomes smaller and it goes inside Roche lobe of the B star. And here it is very close to the B star. It is a very small disk. But despite this, despite being fully under gravitational influence of its own star, the companion star is still able to lock this emitting region, or rather it is emitting because the companion exciting it, even at the late stages of disk dissipation. So the conclusion on the second defense statement is that independently from VNR measurements, Doppler tomography shows a companion-facing emitting region in the outer disk at velocities near truncation radius. The region remains stable, so even when disk becomes very small, the position of it remains intact. And we were able to put some quantitative boundaries on the dissipation process, and the disk contracts from approximately 64 solar radiuses to 30 solar radiuses. And thus the phase-locked VNR ratio arises from this companion-facing outer disk emitting region, which is consistent with tidal and or radiation influenced by the companion star. Now, the second object of my study is called HD698. It is a very interesting B binary because the companion star is kind of in an evolutionary transition phase where it is bloated and spectroscopically visible. So in the object HD698, the central emission peak in the H-alpha line profile is not associated with the circumstellar disk of the B star, but rather with an additional source of radiation moving at velocities close to the companion star. And the companion star has a mass of 1.1 solar masses, which we determined. So the procedure was the same as for Kappa Draconis. We take radial velocities of absorption lines, and they show us this red curve. But we were able to identify that this red curve belongs to the companion star rather than B star. And we were able to find the second data set of radial velocities, which belongs to the B star. It is found from the wings of H-alpha. Now, if we look at the motion of H-alpha as a whole, not only the wings, it will show the same radial motion as the companion star, so the red one, which allows us to think that there is an emission component that is associated with the companion star. And if we model it and remove it from line profiles, then first we get a double peak profile, and we can measure this VNR ratio for H-alpha and compare it for H-beta. They are phase-locked with the orbital motion, and then we can perform Doppler tomography on the original H-alpha profiles with extra emission and on the profiles with removed extra emission and compare them. So we can see that the regional profiles tomogram shows us a complex emitting structure, which is associated with companion star velocities. So not only the disk is influenced by the companion like it was in Kappa Draconis, there is an extra emission that belongs to the companion star. Let's note here that the mass of the companion in this system is almost 3 times bigger than it was in Kappa Draconis. But what's most interesting is the radius that we obtained with modeling. The radius is 13 solar radiuses, which means that this relatively low massive star is very bloated. So it has a big Roche lobe, and it is a possibility and a hypothesis that the matter from the disk is transferred to the companion star. So the conclusion on the third defense statement is that we see on the RV curve that the extra emission peak in H alpha matches the companion's motion, and we were able to constrict the masses in the system, and the mass of the companion is 1.1 solar masses. And in Doppler tomography, we see that original profiles exhibit a compact ridge near the secondary velocities. And if we subtract that extra emission that we talk about here, the tomogram shows us a circular structure with a single emission region that we expect from a circumstellar disk. The restored H alpha profiles show VNR ratio that is phase locked with the orbital motion, and it confirms that the asymmetry of the original profile is contributed by the companion linked emitter rather than being an intrinsic inherent disk structure. So let's recap the results of the study. The Doppler tomography was applied for B stars, and this approach can be cold tested, and it provided some unique insights on the disk structure in the systems. For the Kappa Draconis, we learned that VNR ratio is phase locked with the orbital motion throughout the disk dissipation event, and also for Kappa Draconis, the source of this change in VNR ratio is companion facing outer disk region. For the second object, the narrow H alpha component moves with the same velocities as the companion star, and if we subtract it from the H alpha profiles, we restore the shape of the circumstellar disk. For HD 698 masses were determined for both components, which helped to disprove the black hole hypothesis that was around for the system for almost a century. Results of this work are published in 3 Q2 papers. 2 reports were made at international conferences, and the Q1 paper is accepted. Oh, it's actually been published last week. Here are publications that my defense is based on. I'm the first author in the 2 of them, and that's it. Thank you very much.
Okay, thank you. So the presentation is over. Other questions, comments?
Can I ask a question?
Nazar, can you hear us?
Now I can hear you. Okay. So is it the floor is open for questions?
Yes, yes.
Okay. First of all, Ilfa, thank you very much for this very nice, very clear presentation. It was a pleasure to participate. And congratulations on these nice works. So I wanted to ask a question about, let's say, broader implications of your work. You showed your results very well, but what are broader implications in terms of when it comes to understanding astrophysics or physics of maybe stars, stellar evolution, or binary interactions? I don't know. Thank you.
So I'd like to answer this question in two parts.
I cannot hear very well. It's a bit far away from the microphone.
Yeah.
Okay, so I'd like to answer this question in two parts.
It's good now.
I'd like to answer this question in two parts. The first part is possible application of Doppler tomography to other B stars, as well as other long period massive binary systems. So we now have a full methodology from obtaining data to constructing Doppler tomography. There is a methodology manuscript for the students being published by Kazno on this work. So hypothetically, we can apply this method to any system, to any binary system with sufficient spectral coverage. Now, for the second part of this question, the actual understanding of the physics, from my point of view, the thing that would make this work complete is modeling of the disks, which can be done by, for example, smooth particle hydrodynamics, which I plan to do in the future. When we do the modeling, like, let's say hydrodynamics modeling, we get distributions that we can produce either in spatial or in velocity coordinates, and then directly compare with Doppler tomography, which is based on real data. That's it.
Okay, thank you very much. Maybe one technical question. You mentioned smooth particle hydrodynamics. Why it has to be smooth particle hydrodynamics code? Why cannot be, let's say, standard finite volume code? Is there any specific reason?
The smooth particle hydrodynamics is established as a golden standard for disk in any binary stars, I think. There are great code packages like Phantom and such that can be applied to any systems, and they are open code. You can further develop them. So I think it's a combination of being convenient technically and providing substantial physical results.
Okay, thank you.
Thank you. Thank you.
Yes, Alexander Vladimirovich.
Hello, everyone. Hello, Ilfa. Thank you very much for this presentation. Can you hear me well?
Yes.
Okay. If I properly understand this, the tomography you are using as a tool, it's a kind of inverse problem techniques. So do you have some plan in future, for example, when you show these maps of reconstructed velocities and locations of, for example, some emission region, etc., to provide us also with a kind of map of resolution, because we know that when you try to inverse the problem, to solve the inverse problem, you will always have some kind of area from which you resolve, try to show us the result. So as I understand, these maps you show, they always have some kind of varying resolution depending on the position on the disk. It's just a question about the future development of your software. Do you have anything in your plan to develop these kind of things? Thank you.
Thank you. So if I understand correctly, the possible problems with Doppler tomography, they come from when changes in the disk happen at periods smaller or much bigger than orbital period. So then they get smeared out in the map, and we cannot clearly identify them and describe them. So the solution to that would be actually tricky, because orbital period is like period by definition. But if we say know at which period exactly the change is happening, then we can convert Doppler tomography with this period and see what it shows. Maybe isolate the change in structure and overlap it with orbital period one. I hope I answered your question.
Yes, thank you. It's really the case when you smear out this the map due to the rotation. Another issue is the mathematics itself, okay? Because when you try to reconstruct anything with a limited information, you definitely will have some smear out resolution in your disk. So probably in future, when we will collaborate, we will talk about this, okay? Thank you.
So to comment a little on the mathematical side, the Doppler tomography as it is implemented now uses the maximum entropy principle. The entropy here is informational entropy, which tells us how much information each pixel has. And then we try to minimize then we try to minimize this expression, which should give us the optimal image. Like, it's not actually for a specified chi-square level. So we don't minimize chi-square, but we minimize the entropy in the image, which is, yes, one way to do it. There are definitely possibilities here. That's a great suggestion from you. Thank you.
Oh, okay, yeah, that is exactly what I want to see. Thank you very much. Perfect. Jonathan, right hand, still waiting here. He's still waiting.
Yes. May I ask a question or two? Oh.
Probably
Let's
they
see.
are not hearing you.
Can
There was a
you-
question by Jonathan. Can anybody hear?
Yes, is my audio working?
I can hear you, Jonathan, but I don't think the audience,
okay.
this hall is hearing it.
Okay, please ask you.
Yes, you can hear me now?
Yes.
Okay, good. First, thank you for the presentation, and it was nice to reread your papers and catch up on things. So just first, two brief comments. I think that this technique of Doppler tomography is underused in our field, and I appreciate your efforts to apply this to useful binary systems. And I found your research on HD 698 to be very interesting and novel. It's a unique pair of papers on this. So if I may ask one or two specific questions about the HD 698 system.
Yes.
So these are topics that weren't covered in your presentation, but are described in the paper. So the first question is, in your modeling of HD 698, you assumed that the BE star is near the terminal age main sequence, right? So I was wondering why you chose a slightly evolved age for the BE star in this stage that is what we think shortly after mass transfer.
Okay. Yeah. I just looking for a right plot. Here, if we look at the Hirschsprung-Russell of the system, it has a lot of interesting things, but to answer this question, the purple star is the B star, and the big green circles are known B stars in binaries with SDO components. So our B star falls close to the general population. So of course, it is not safe to say we're 100% certain it is at the end age of main sequence, but for all the purposes of modeling that was focused on the companion star, it did a good job. It didn't find any contradictions that would tell us that this assumption was wrong. That's all I have.
Okay, good. Yeah, I like this answer because it actually challenges a lot of our default assumptions about these post-mass transfer binaries. A lot of works call the mass gainer in these systems rejuvenated and assume that a lot of mixing takes place inside the star and brings hydrogen into the core. But I think we don't actually know what the mixing processes are. So this is an interesting result that the star appears slightly more evolved than zero age main sequence mass gainer.
Yes, we will definitely need to do more advanced modeling of the B star.
Good. Okay. And then one more quick question is, in the paper, in one of the tables, you have a value for V sin I of the BE star, again for HD 698. And I was wondering how you derived that value for the rotation velocity.
It comes from the same assumption that you originally asked about. We modeled the B star using Geneva evolution tracks, which are publicly available. So by given mass, the mass we are very certain about, we get this rotation velocity.
So do you have any spectroscopic features like absorption lines that you see from the BE star?
No. Spectroscopically, if you're talking about absorptions, none of the lines showed the motion other than the companion star.
Right. And just connected to this, are there any other emission lines besides hydrogen that you could use? If you measure the peak separations or some emission features like from helium or some metal lines?
Sorry, I missed the beginning of the question. Is this related to Doppler tomography?
Possibly. Are there any emission lines besides hydrogen that you could use to perhaps apply Doppler tomography or try to constrain the V sin I based on like peak separation measurements?
Yeah, okay. So for HD 698, we only have H alpha in clear emission, and it has very complex profile. Like I showed, there is extra emission that needs to be very carefully removed to obtain double peaked structure. There is also H beta line, which is deep in absorption, but it has emission peaks measurable. But then we will probably need to carefully remove that absorption as well.
Yes, right. Okay.
There are not many options to do what you suggested.
I see. Okay, thank you.
Here is the H beta profile. So I cannot be sure that these peaks are pure emission, like the separation isn't affected by absorption components from both stars. So not sure.
Okay, good. Thank you.
So okay. The decretion disk is formed not by accreting mass. Like if you are talking about accretion disks, we have the mass transfer flow from one star to another, and because of the angle at which matter falls onto orbital plane, it forms the disk. But here we don't have any kind of mass transfer going on. What we have is the B star rotating very fast near critical velocity, and we know that it sheds matter onto the equatorial plane and forms a disk. The thing we cannot tell for certain is this caused by rapid rotation alone, or do we need additional mechanisms? The most popular additional mechanism is called non-radial pulsations, which would need to be aligned with the equator of a star to eject matter into the disk.
It seems because in your paper you mentioned that this star rotates 70% of the Keplerian angular velocity. It means that it cannot shed at this rate, even if it rotates with this frequency.
Yes, so it's one of the mysteries of B stars, because there are fast rotating stars that don't form disk, therefore they're not B stars. But there are also stars with these non-radial pulsations that I talked about that also do not have disks. So a B star probably must have both. So it must rotate near critical velocity and then have non-radial pulsations on the surface. And when we have a non-radial pulsation on equator, then it injects mass into a disk. But that's not an established theory.
Okay. And why there is asymmetry between violet shift and red shift?
So if you look at this picture, this is a schematic image of a disk, which has a density enhancement. We don't know like what exactly it is, just a region in the disk that has more emitting particles than other parts of the disk. And if you look at it at phase 0.5 directly, then we will see how line profile mirrors, like shows us that there is this disk enhancement present in the disk. And then if you look at it at the other phase, in this example 0.25, then we cannot see the enhancement we cannot isolate it, but we can see its contribution to the upper peak or right peak if you rotate the picture. And if you would look at phase opposite of that, so 0.775, you would see that the other peak is actually bigger, because at this moment of observation, you see the system at this point of view. And that's why we need as dense phase coverage as possible of observations to be certain what we actually see.
So, but what causes asymmetry?
The natural thing to occur in disks is the spiral arms. So you would have a dominant spiral arm and a trailing one, weaker. So the emission that comes from the dominant spiral arm would show as what I show here as a black spot. So then looking at its position, that it is oriented at the companion star, we can suggest that it is gravitationally or radiationally affected, or like particles are excited by the companion star more than there are other emitting particles in other regions of the disk. So we can see this emission feature here.
Okay. So in your second conclusion, you mentioned about contraction of the disk radius from 60 solar radius to 30. Yeah. So what causes also this contraction? Because this contraction is huge, twice, I mean, decreases the size of the accretion disk.
So
can you just tell what is the time period for this process to take place?
The numbers of disk radius are average values for the chosen time periods of observations. So 64 solar would be for the first period of observation, 3 years, and 30 would be averaged over last 3 years of observations. And the process of disk dissipation is supposedly, like I can't say that it is true, but we can suggest that the star stops ejecting mass into the disk. So the disk dissipates outward, like particles from outer edge go out of gravitational bounds of the star until there is no matter left in the disk. And some of the inner edge particles, they fall back onto the star. Either way, disk just stops to exist.
Okay. Thank you. So are there questions? Dana, please, you should ask at least one question. You are the reviewer official. So you are the only person who is left.
Yes, sorry, it's just because I had this background music, so I wanted to avoid some noise for you. Yes, I asked some questions when Aoife presented me her research before the submission of the reviewers' comments, but I can also answer some of the questions now. Info about the Kappa Draconis project. So this violet to red variability, you observe this for multiple years. Just a small question. So it's been, you were not the only observer, right? Did you observe, what did you observe by yourself?
Mm-hmm.
Great question. Because I didn't observe any of the spectra. It was not part of my PhD program.
Okay.
I was focused on
not a problem.
processing data, analysis, and modeling.
Okay, and the tomography that you used was also developed before you, or did you develop the tomography?
It was developed by people called Marsh and Horn in year 1988 in this paper. So
Okay.
the unique part in this work related to Doppler tomography is application it to B stars, because this method was developed and most commonly applied to cataclysmic variables, which are quite different systems. They have very short orbital periods like ours, and they have active mass transfer going on. So the application of this method to B stars required some careful consideration.
Related to this question, so did you code the, so there was a method developed by Marsh and Horney, and then you wrote the code to apply it, or the tool was already there?
The
theoretical
tool
tool.
was there. We did enhancement, but
You improved the tool?
yeah,
You mean-
modifications of the code to apply to B stars.
So you did it. Okay, thank you. I don't have any other questions.
Okay, thank you. So if there are no further questions, so the floor is given to the foreign supervisor, Doctor of Physical and Mathematical Sciences, Professor of University of North Carolina at Greensboro, Professor Miroshnichenko Anatoly Sergeyevich. Yeah.
What should I say? So there is my
Just recommendation, just description. Yeah.
From here, or?
Yeah, you can speak there.
Yeah.
No problem.
All right. So this area is a developing area in astrophysics. Only 20 years ago, most B stars were considered to be single stars. And the advent of multiple spectroscopic observations showed that in some stars you can see regular changes of the absorption lines, which is a direct evidence of binarity. And in some of them, we see things like what Ilfa analyzed, the variations of the typically hydrogen line profiles, because hydrogen is the most abundant element in the universe, and the hydrogen lines are the strongest lines in the spectra. This method was previously mostly applied to accretion disks, and the first application was done about 12 years ago to 1B star, and we actually, Ilfa, and with the help of observations from our observatory and from amateurs, showed that this method works in other stars. So now it will be applied to more objects with various periods, and we will see how the orbital period, which means the separation of the two stars in the system, and the mass ratio affect the disk, the development of the disk, the cycles between no disks and active disks. So that's a very important area which hasn't been explored, and Ilfa's work is a very convincing beginning to it. So now we can expand it, and this will, I believe that this will give us some more insights into formation of the disks, and we will find a wide variety of cases, which means that you know this is not a very short period, because there are many B stars. They are located at different evolutionary stages, both primaries and secondaries. So when we have statistically significant sample, it will definitely contribute to our understanding of evolution of intermediate mass stars, and in particular to binary systems. So I think that this is a very important work, and it has a great future.
Okay, and your recommendation to the candidate?
Recommendation in terms of what? In terms of the
Do-
extension of
Do you support her?
Yes, absolutely.
Okay.
Yeah.
That's important.
And it actually shows that the observations which can be analyzed with this technique can be done at relatively small telescopes with relatively cheap spectrographs. So it can be done at more observatories and cover many stars, because only within 1 kiloparsec from the sun there are about 500 V stars, and these are just single examples of the brightest ones, which obviously set a stage to expansion work. So I hope we will work together on some more objects in the future.
Okay, thank you. Now the floor is given to domestic supervisor, Khakhlov Azamat Anatolievich.
Speak short. He will present the clear and well-structured study that demonstrates good research skills and sought to analysis. The legal team shows good command of subject and uses property methods to address the research questions. The material is present correctly, and the results are direct and logical and unstable. Overall, it is a compliment and well-prepared piece of also works. In my opinion, the dissertation fully meets all requirements for the PG degree in physical astronomy, and represent and meaningful and original contribution to such fields.
And your recommendation?
Recommended.
Okay. Okay, thank you. Now we will proceed to the discussion. So the floor is given to official reviewers. So the first one is Serebryansky Alexander, PhD, leading researcher at Fesenkov Physical Institute. So,
Hello. Okay, dear members of Dissertation Council. Well, first of all, following the absolutely pertinent comments by Anatoly, I would say that we usually deal with kind of laboratories and experiments in the heavens, right? So these laboratories and experiments, they are designed for us to test some physics. So we can't control this, the path of experiment, and those labs are working because they're far, far away. So we need to be quite smart to interpret what we actually see and what we actually try to infer. So it was done at high quality in this dissertation, I think, because IDFA, she mastered the math methodologies, will deeply understand the physics which is govern the process behind these stars. So this definitely will open many doors in her future research. And every time when you try to use some new methods and new technologies, and even in well-known some, I will say, laboratories or experiment, they will definitely bring some new knowledge, some new insights in the physics, and especially in the binary stars and stellar evolution. So in her dissertation, she provides a qualitative and quantitative description of a complete B star disk dissipation event, for example, through the Doppler tomography. And she identified and provided kinematic characteristic of a narrow emission lines component, which is co-moving with the companion in the stars, and established direct self-consistent constraints on the companion mass, for example, in the HD 698. So I think what should I also mention is it provides a reproducible, end-to-end methodology for analyzing B stars, especially binary in B stars, including standardized line measurement, for example, period analysis, phase result tomography. I think this is very important to mention that in this thesis she provides like a tool, so other people after her and she itself will, repeat this kind of procedure for another stars, another process in another, well, not just in a B star, maybe something else. So this dissertation, which is titled like a structure and evolution of circumstellar matter in B stars, it satisfies all the requirements standards established by the Committee for High Quality Assurance in Science and Higher Education of Republic of Kazakhstan to award Doctor of Philosophy, PhD degree. So I think Gabitova Ilfa Azamatovna is fully deserving of the academic degree of Doctor of Philosophy, PhD. So that's my conclusion. This work is for sure at the level of PhD dissertation. Thank you.
Thank you very much. Okay, now the floor is given to the second official reviewer, Alina Dana, PhD, Assistant Professor of the Department of Physics, Nazarbayev University, Astana, Kazakhstan.
Can you hear me?
Yes.
So if Gabitova's presentation is based on the 3 publications, the presentation was done in a coherent manner. Ilfa is the first author of 2 of the 3 papers that were presented. All the conclusions of the dissertation are based on observational evidences, and Ilfa has produced numerical work to make the analysis. The quality of the presentation was very good and very clear. The dissertation has clear scientific and practical significance. She developed an applied tomographic approach for the B star systems. She determined the mass, and she could rule some hypotheses, such as the black hole hypothesis, and showed analytical works in comparing the theoretical and observational data. Should I read my review or not? Like the one that the official that I have sent.
You should just read the last part of your
Okay,
review.
just the last part.
Yes. Mhm.
Okay. This is dissertation work of Gabitova I.A entitled Structure and Evolution of Circumstellar Matter in BFAS meets the requirements of the Committee for Quality Assurance in Science and Higher Education for dissertations for the degree of Doctor of Philosophy. The candidate deserves to be awarded the academic degree of Doctor of Philosophy in the educational program AD 05307 Physics and Astronomy.
Okay. Thank you. So, dear colleagues, each of the official reviewers has expressed their opinion, and I hereby conclude the discussion and give the final word to the candidate. So you.
First of all, thank you to all of you who showed up for me here today. For some of you, it's nighttime. For some of you, it's still Sunday. So I really appreciate this. And thank you, Anatoly Sergeyevich and Sergey Viktorovich and Alex for teaching me and mentoring me, guiding me from students' work to real science. And thank you, my dear colleagues, for always supporting me, being there for me during these 3 years and making it fun. That's it.
Okay, thank you. So, with the opinions of all official reviewers, now allow me to open the general discussion. So, dear colleagues, who would like to speak just a few words about the work, about ILFA, about, let's say, prospects of this research, or some wishes?
I just want to congratulate Ilfa on her work and on the quality of the papers and the quality of the presentations that showed. She is a young scientist with big perspectives.
Okay, thank you. Is
Can
there
I-
anyone?
Yeah,
Yes.
first of all, I hope we will see in near future more papers in Q1 from ILFA. And I hope even in Nature maybe someday. So I wish her a very, very nice future in this kind of research, in this kind of direction. And I hope we will have more meetings in this discussion, this tomography, maybe some expansion to other objects, and maybe using our observational data from our telescope in Kazakhstan. We will discuss this. I hope it will be very nice work in the future.
Okay, thank you very much. We also hope, because to publish paper in Nature, it is a great success, I believe. So, is there anyone else to speak, to talk? Okay, if there is no one, so thank you for everyone. We now proceed to the next stage of the council meeting to conduct the secret ballot. The floor is given to the scientific secretary, Turikhanova Kunduz.
Okay, thank you. Dear members of dissertation council, the ballot for secret vote has been sent to your email. Could you check please your email and please cast your votes? Have 5 minutes.
Okay, as soon as they finish, we can continue.
When was it sent, this email? Just now?
Yes. Получить?
Yes, yes.
Да, да.
Okay.
Refresh your email. I think you should have.
Okay, just received. Thank you.
Mhm.
Да.
Mhm.
Девяточка.
Добре. Okay.
8, 9, вот еще.
Okay, one person is missing. Mm. Yeah, yeah.
Можешь сказать там?
Have you voted?
А всё.
Okay, that's it. So thank you. We now proceed to the next stage. So to announce the results of the secret ballot, the floor is given to the scientific secretary. Rihanna Kunduz.
Okay, thank you. Allow me to announce the results of secret ballot. All members of the dissertation council have voted. Results of secret ballot awarding for the degree of Doctor of Philosophy PhD 9, and the submission of the dissertation for revision 0, submission of the dissertation for repeated defense 0, refusal to award the degree of Doctor of Philosophy PhD or Doctor by proposal 0, and the results are certified by an electronic Excel document. Here you see all of it.
Yeah.
Here it's the Excel results, and here you see that all here
100%.
100% awarding the degree of Doctor of Philosophy PhD.
Thank you very much. So, within the framework of the Dissertation Council of Al-Farabi Kazakh National University for the specialties and educational programs, physics, technical physics, physics and astronomy, material science and technology of new materials, thermal power engineering, electrical power engineering, standardization and certification, nuclear medicine, radio engineering, electronics, and telecommunication. So the dissertation council resolves to award the degree of Doctor of Philosophy, PhD, in the specialty AD05307 Physics and Astronomy to Gabitova Ilfa. Congratulations. Congratulations. So now we have the last part of our dissertation council. So in accordance with the regulations, it's necessary to adopt the council's conclusion on the dissertation of Gabitova Ilfa series of articles. So the the draft of the conclusion and the classification characteristics of the dissertation have been sent by email to all the members of the council. So what comments or proposals do you have? All the members, including temporary, including permanent members of the dissertation council. Okay. If there are no proposals, so the discussion and adoption of the council's conclusion and classification characteristics of the dissertation of Gabitova Ilfa. So we accept this draft as a conclusion. And in the end, we conclude the meeting of the dissertation council for the defense of the doctoral dissertation of Gabitova Ilfa, which is hereby declared closed. So thank you very much.
Thank you.
Thank you.
Thank you.
Thank you.
Bye.
Bye.
Bye-bye.
Bye-bye.